All right, here's an example of a 9.3 problem. I chose 9.3 number 6, and you can read it here. It's talking about how they feel a popular theory is that presidential candidates have an advantage if they're taller than their main opponents. And so what they listed out was a group of 6 presidents and their I think there's six. One, two, three, four, five. Yeah, 6 presidents and their heights, as well as the height of their main opponent that year. And it says use the sample data with the zero point zero 0.05 significance level to test the claim that for the population of heights of presidents and their main opponents, the differences have a mean greater than 0. So our claim is nice. So let's go ahead and do part A. We know part A. Part A is, let me make that a little bit lower here. Part A's claim is that the differences in the heights for everybody is going to be, oops, and I'll write the word claim. So here's the differences in the heights for every single presidential candidate, and we want to show that that's greater than 0, which would mean that the president is taller, right? That would test that theory. The null hypothesis would be mu d equals 0, and the alternate would be the claim itself because it can be. We know already that this is a right-tailed test, and that 0.05 is in that one tail. The degree of freedom that we will need, because we know it's going to be a t-score because of the mu, is going to be, well, we have 6 pairs of data, so the degree of freedom is going to be 5. And so look at what we can do. We already know, hey, degree of freedom's 5, 0.05 in one tail, it's on the right tail. So let me go look up 5.05 in one tail is the second to the last column, and I get a critical value of 2.015. I got to be more than 2.015 away. Well, let's go get that test statistic. Well, easier said than done, right? The test statistic for this is d bar minus mu d all divided by s of d all over root n. And we know some aspects of this. We don't know d bar, but mu d is right there. It's 0. What do I mean by right there? I'll underline it, or actually I'll box it. It's the null hypothesis. SD I don't know, but I do know that there were 6 pairs of data, and so that's a 6 in there. Now what do I need? Well, I need differences. So as we go through this, we're going to need to get a difference row. And so I'm going to look at the 185 minus 171 and come up with 14. The first president was 14 inches taller. Then it's 178 minus 180, negative 2. Right? The next president was 2 inches shorter. 175, 173, difference of 2. 183 minus 175 is 8, right? 8 inches. 193 minus 188, and we get a 5-inch difference. And 173 minus 178 is a negative 5. Don't let that negative 5 throw you off. That negative 5 just means that the president was actually shorter. So those will help us. We need to get d bar. Well, those are our d's. Those are our 6 d's. Well, you know how to get d bar. Here's your side work. D bar is equal to the sum of the d's divided by n, or some number divided by 6. Well, let's go find out what the sum of the d's are. It's a 14 plus negative 2 plus 2, right? So minus 2 plus 8 plus 5 minus 5, and we end up with 22 as our sum. So 22 is our sum. 22 divided by 6 is, and they'll round their d-bars to 1 decimal place beyond the original set of data. So 3.7. They'll go back to that chapter 3 rounding rule. But we need also to get S sub d. So the best formula for S sub d is this one. If you're okay, I'm going to go ahead and erase what I did up here just to give me some more room in here, and we'll find S sub d right here. Here's the formula for S sub d, and I'll write it here. S sub d is equal to n times the sum of the d squareds minus the sum of the d's, the whole thing squared, all divided by n times n minus 1. And what you'll find if I do this nicely is that you have almost everything. You know n is 6 because you have 6 differences. You do not know the sum of the d squared, so we're going to leave that blank. But we did find out that the sum of the d's was 22, and we're going to square that. And that's all divided by 6 times 5. So all we have to do is get the sum of the d squareds, and you can start to see why they call this the shortcut method. So what are we going to do? We're just going to square all of our d's. We're going to square 14 and come up with 196. Square negative 2 and come up with positive 4. Square 2 and 4. 8, 64. 5, 25. Negative 5, also 25. And we're going to add that up. We're going to take 20. I'll start with 196 plus 4 plus 4 plus 64 plus 25 plus 25. And we're going to get 318 if I've done that right. So your S sub d is that. So let me just double check that again by adding a second time. And I do get 318 again. So let's go find our S sub d. All we have to do is follow the formula. 6 times 318 minus 22 squared. And I would hit equals, divided by, and in parentheses, 6 times 5. And then take the square root of the answer. And we get a fairly big standard deviation, 6.88. So they'll put 6.9. And we'll put our 6.9 in there. And we're almost done. Now we take our 3.7, subtract away 0, and divide that by, in parentheses, 6.9 divided by the square root of 6. And what do we get out of that? We get a t-value of 1.313. Well, that's not big enough to reject, and so we fail to reject our null hypothesis, and so the data is not strong enough to support our claim, right? Our claim that mu d was greater than 0. We have not been able to establish that the presidents have a higher height, are taller than their main opponent. They are asking us to do B, which says to construct a confidence interval that could be used for that. Well, we want to use the same 2.015, so just like our work in A, if we use that 2.015, we realize confidence intervals are two-tailed. So we're finding the 90% confidence interval, right? Because there would be a second 5% if we put in the negative 2.015 and 2.015. And so if there's 5% here, there's 5% down here, which means 10% is accounted for. So we get 90% in the middle, just like in our chapter 8 days. So how do we get this? Easy. We take d bar and add and subtract our error. We're really done because we've done a lot of the side work. D bar was 3.7 if you remember. I can scroll up. But we had d bar as 3.7. And then the error is, so it's going to be 3.7 plus or minus the error. What's the error? It's a t alpha over 2 s sub d all over the square root of n. Well, we know all those numbers. This is 2.015. S sub d is 6.9. And n is 6. And so we take our 2.015, multiply by 6.9, divide by the square root of 6. And what do we end up with? We end up with an error of 5.676, or 5.7 if I round it to the same level. So what's my confidence interval? Well, it's 3.7 plus or minus 5.7. So if I take 3.7 and subtract away 5.7, I get a low value of negative 2. Remember, this is a bound for the difference of all the presidential heights. And if I add it, I get up to 9.4. So that's why we're not able to reject the null hypothesis, because mu d really could be zero. That's why we're not able to establish the claim, because the claim may actually be false. It could be true, but it could be false. And so that's what these problems feel like. You'll do this side work up here to find S sub d and mu d, but doing those problems together, there's a lot of overlap in there that makes the problems really, really nice. So that's your main example for 9.3 is this number 6. Hopefully it was understandable.